All right, team. My goal of this video is to help you get from good to great. We worked on finding the derivative by definition yesterday, and there was a lot of heavy algebra involved. A lot of you got there. Some of you need a little more support. For all of you, this is going to help to drive the idea home. But first, let me start by just defining everything that we have. So we are working on calculating the derivative. And the derivative is the exact instantaneous rate of change at a particular moment in time. So we've already worked on this. We did it through estimating instantaneous rate of change. And we used a change in time of 0.01, which is very, very small. It's a hundredth of a second, which the human eye cannot detect, but it's still not an instant. So now we're going to look at how derivatives really tie everything we've been doing together so that we can find how fast something is going at a particular moment in time. What we're going to use to do that is this definition of derivative. It's a limit definition. And so what it's saying is that if we have a function, we want these 2 points to get infinitely close together. So we're saying x needs to get infinitely close to c. So they're basically the same thing. So we are getting them closer and closer together. And what we're saying is to get instantaneous rate of change, we can use the rate of change formula. We just have to make that change in time infinitely small. Not just 0.01 anymore, infinitely small. So for this example, it's very similar to yesterday, but different, and I hope this will help solidify the ideas. I'm going to use the function f of x is equal to x cubed. Another way to write that function is y equals x cubed, just two different notations. Now, just like yesterday, if I want to find the limit of this function, the derivative, using the limit definition, what I'm going to do is I'm going to replace f of x with the actual function, and then I'm going to substitute c in to f of x to find f of c. So what that would look like, the limit as x approaches c, where I have f of x, I'm going to substitute f of x. So that's x cubed. Where I have f of c, I'm going to plug c into this function. So that means instead of x, I put c in its place. C cubed is c cubed. Because it's some constant, we just don't know what constant. And in the bottom, we're going to leave it as x minus c. Now, with limits, you can always plug the value in. So in this case, it's c, and we can see what we get. So if I were to plug c in for x, I'd get c cubed minus c cubed on the top and c minus c on the bottom. That's 0 over 0. And like we talked about today, that is never an answer. It is a big, fat, flashing red light saying, simplify me. I am simplifiable. And your strategies for that, you can do long division, you can do Polyduco, you can do whatever your heart desires. And I know it is trickier when you have variables versus actual numbers, and I know you can do it as well. So what I'm doing is I'm taking this right here, and I'm taking x cubed. Erase that. And I'm going to divide it by x minus c. Now, I don't know exactly how far this is going to go, so I'm just going to start it, and I'm going to work from there. So if I have a generic rectangle right here, and the area is x cubed, I have x on this piece, I need x squared right here. That's how I get my x cubed. So then over here, my dimensions are x squared by negative c, or the opposite of c, so that's negative cx squared. Now, when I go up here, I notice that I don't have any cx squared terms, so I need to get rid of that. To get rid of that, I would just have the exact opposite. All right, so then I know the dimensions of this rectangle are x by something. To get cx squared, it needs to be cx. So now I have the dimensions of this rectangle. I have the negative c times cx, which would be negative c squared x. And then just like last time, I look up here. I don't have that negative c squared x as a term, so I'm going to do c squared x to get rid of that term. So I know this dimension is x, which means that this needs to be c squared. And now I have the dimensions of this rectangle, which gets me negative c cubed. And that is what I have up here. So the beauty of this is these two are equal and opposite, and they cancel. These two are equal and opposite, and they cancel. So what I've just done is I've taken x cubed minus c cubed, I've divided by x minus c, and right over here I have my answer. Now, that is just simplifying this rational function. I've divided using Polyduco. So now I have a new limit statement. The limit as x approaches c of x squared plus cx plus c squared. Now, in an algebraic limit, I take the value and I plug it in. So I have the limit as x approaches c of c squared plus c times c plus c squared, which is c squared plus c squared plus c squared, which is 3c squared. So what it's saying is when I start with a function right up here, f of x is equal to x cubed, the derivative of that at any constant, and that's what c is a constant. The derivative at any constant is 3 times the constant squared, right? Now, let's say we don't know what the constant is. We can put x in its place. It's 3x squared. So when I started with x cubed, my derivative, notice the notation right here, that's the symbol for derivative, is 3x squared. Now, that is a whole lot of work. And if we had to do that every single time, it would be miserable. And so thankfully, when you're paying attention here, you might see a little bit of a pattern. So over here, it was cubed. Over here, it is squared. Okay? And here, this exponent came out front. And that is the power rule. All right? The power rule is like, no joke, the most powerful thing in calculus. And it just says that if you have a function, so let's say it's y equals a, or a is some number, x is a variable, and it's being raised to a power of n. The derivative of this power function has to be a power function, so an x, a quantity with x raised to a power. The derivative always follows the pattern where you bring the power down and you multiply it, and then you go to one less power. Now, I know you don't really like it when it's a whole bunch of variables, so let's look at some tangible examples. All right, let's say we have y equals, let's do x to the 6th. Right? The derivative of that, y prime, I bring the 6 down, I go to one less power. Boom shakalaka, I'm done. None of this junk. Bleep. All right, so that's a really basic example. It's going to get more complicated in a variety of ways. So it can get more complicated by having multiple terms, which you're probably like, that's not too crazy. It really isn't. So let's say we have 3x to the 5th plus 6x squared. The derivative of that, I'm just going to take it one at a time. So I've got my term 1, I've got my term 2, I've got a plus in between. So my derivative will have a term 1 and a term 2 and a plus in between. So the derivative of my first term, I bring the power down and multiply. 3 times 5 is 15. I go to one less power, gets me to 4. So the derivative of 3x to the 5th is 15x to the 4th. Next one, I've got 6x squared. I bring the power down and multiply. That gives me 12. I go to one less power. That gets me to x to the 1st. But because it's the first power, I don't actually have to write that one there. I can, I don't have to. Right. Now, a couple more things to remind you of or show you, and then also kind of some extensions that may push you a little bit. Let's say we have 6x to the 4th plus 15 for our original function. So we are still going to take the derivative of both terms. So I've got two separate terms. I've got my term 1, I've got the plus in between, I've got the term 2. Now, the derivative of the first one, I bring the power down and multiply, that's 24. I go to 1 less power, that's cubed. Now, there are a lot of different ways to look at this. It is a constant, which means it is something that always stays the same. All right, if I were to graph this, I go up 1, 2, 3, 4, 5, 6, 7, whatever. We'll just call this 15. It would be a straight line at 15, a horizontal line, which has a slope of 0, which means the derivative, because it's the instantaneous rate of change, because it's the slope at any point, is 0. Another way to look at it is it's like you have x to the 0 power. So when you bring that power down, that becomes 0. So the derivative of a constant is always 0. So you don't need to write that there. Your final answer would be 24x cubed. Now, again, to preview, the things that are going to give you trouble, these first ones, they're pretty straightforward. Where it gets trickier is when you have negative exponents. Okay, so let's say you have, let's do 3x to the negative 5th. If we want to take the derivative, it's still the exact same thing. That power rule applies to all power functions. But see if you can guess where the mistake is. So what a lot of people will tell me the answer is x to the negative 4th. And that is a big fat no-no. And here's the reason. Every single time we do this, we bring the power down, we multiply, and we subtract 1. And negative 5 minus 1 is negative 6. All right, so that would be your final derivative. If you're looking for a challenge, you should try problems that are going to involve a rewrite. So let's say we had 5x squared, and you were asked to find the derivative of that. It's a fun one because first, yeah, I know, a weird idea of what fun is. 2x to the negative 2/5, and then I have to take the derivative. All right, I'm going to leave you hanging on that one. So thank you for watching through this. Let me know what questions you have. I'm here to support you. Ready, set, be awesome.